Good morning, everybody. I welcome you to CS Katha Barta. We invite academics and professionals to deliver their talks here. And our guest for today's talk is Tanay Narshana. He is a machine learning engineer at Google and he completed his master's and undergrad degrees from IIC and IIT Rupert, respectively. He's going to talk about structured pruning of neural networks without access to training data today. Tanay, I welcome you to CS Katha Barta and I invite you to take the virtual stage and begin your presentation.
Sure. Uh, Thank you for inviting me. Uh, uh, yeah, and feel free to stop me in between. I love having a discussion, so as I go through the content, feel free to stop me in between and just ask me questions. And yeah, so this work was done while I was a master's student, and the work was supported by AMD, and well, I now work at Google, but yeah. Okay, let's begin. So, structured pruning of neural networks without access to training data, a mouthful. Uh, let's break these and into chunks and understand what we're trying to solve here. Uh, so, an important concern that a lot of people in deep learning per se have is that the way we are scaling models, the compute that is going to support both training and inference of these models cannot keep up with this increasing scale. So Moore's law simply cannot keep up with deep learning. This is what was the takeaway of this particular manuscript. Uh, on top of that, the carbon emissions that are generated by deep learning models, both training and inference, is just too much. Apparently, just for one iteration of or one fine tuning of BERT, it I think takes uh, somewhere comparable to an entire car's lifetime. Just one uh, ablation study for BERT, and BERT is no more a large model nowadays. So that is what this manuscript had to say. And this is not where the story ends. Uh, for NVIDIA CEO, approximately 80 to 90% of the cost of machine learning in terms of hardware costs is devoted to AI inference. And this is an important chunk that needs to be reduced. And not just for this, but even to democratize AI. So if AI is too costly, folks who are in underprivileged areas might not be able to afford all the good things that it brings with itself. Uh, right. So we focus on the inference bit of things. How do you reduce the inference costs? And with larger models, deep neural networks are challenging to deploy. Nowadays, a large language model cannot be hosted on a single GPU. We require tons of GPUs to just host a single model to get it to generate a response. Uh, Simply because it has high storage requirements, and even if you try to bring it to a very small GPU, the latencies are still very bad. Uh, so one way to kind of uh, mitigate this issue is pruning. Other ways are distillation, quantization, low rank decomposition. I'll not be focusing on those, I'll just be focusing on pruning. And within pruning, I'll be focusing on structured pruning. I'll come to what is structured pruning precisely and how is it different from other ways of pruning. But in essence, structured pruning is removing unwanted neurons or channels from a neural network. When I say neurons, it is this traditional neuron, and channels refers to mostly vision models. Uh, and we remove these neurons entirely. And For example, if you have a neural network, so throughout this presentation, usually neural networks are depicted from left to right, the initial layers at the left and the later layers at the right. In this presentation, wherever I depict a neural network, it's from top to bottom. The initial layer is at the top and the later layers are in the bottom. Uh, so if you have a neural network, just a subset of a neural network, and you want to do structure pruning of this particular neuron, you have to remove all of these associated weights in red. So consequence of structure pruning is that you are actually reducing, you're physically reducing the number of parameters, and you're physically reducing the amount of compute required to kind of make an inference. So yeah, and this is an, if you have stacks of such layers, that is a single branch network. I'll tell you why this is important later. Uh, So if you're aware of a network like VGG, VGG is a single branch network. So why structured pruning? So if you look at the weight matrix of a standard neural network, you see that structured pruning would have an entire neuron being removed at once, whereas something like a block pruning would have blocks of uh, weights being removed at once, whereas unstructured pruning has uh, uh, a very high sparsity of what I mean by sparsity is that you can remove any single weight. But the good thing about structured pruning is you are physically reducing the size of matrices, and you do not actually require any specialized software or hardware to accelerate networks when you're actually reducing the size of matrices. So which is why we focus on structured pruning. And uh, in general, pruning pipeline has three steps. So what happens is, in the first step, you try to decide which neuron to prune. So using some fancy or very simple math, you try to deduce how important a neuron is. So for example, here I am associating a score with each neuron. The lower the score, the less important it is. Uh, these are some ways to do it. We'll not dive deeper into it, but the lower the score, so this is the lowest score. So in the next step, we'll try to discard this particular node, and in the process, we'll remove all these weights. And once that weight is removed, we'll try to fine tune the network, because removing this node might have led to loss in accuracy. So this is a very standard pruning pipeline. Uh, However, here the scoring step and the fine-tuning step both usually require access to training data. However, for security and competitive reasons, folks who make their models usually do not release their data sets that the model was trained on. So this raises a natural question that, can we prune networks without having access to the data that it was trained for? Uh, Yeah. On top of that, fine tuning is expensive too. So if you do not have data and you cannot fine tune, can you still prune networks? Right. So in this scope, we try to address two problems. Uh, First is, can we improve the inference time of models on hardware when we do structured pruning? And second, if we do not have access to training data, can we develop statistical methods to understand how to prune the network? Yeah, any questions until now? Okay, I'll move forward. So let's first go over how do we improve the performance of models on hardware. So this is the first work that we'll talk about, which is data flow driven pruning of coupled channels without data. So the key here to is to focus on the term coupled channels. We'll see what that is. Uh, yeah. So most modern day neural networks usually have what is called uh, a residual connection or a layer skip connection. So why is that often used? So if I remember correctly, this is the most highest cited paper in any field, which introduced the notion of residual connections. So the problem with deep neural networks was that the gradient used to explode or vanish as you do backpropagation uh, from the lowest layer or the deepest layer to the initial layer. And to prevent that, people used residual connections where you would have say a layer at layer I and a layer at layer J. Both of their outputs would be added and fed to a different layer. So this would mitigate the problem of vanishing and exploding gradients, making the training more stable. And this is a very common use practice. So the challenge of pruning, so what we say is that we call such a setup as coupled neurons or coupled channels for vision networks. And why so? So let's say that you want to prune this network, uh, which is connected to, which is fed into a residual addition. Since this is a vector of size 4, this is a vector of size 4, and you can only add vectors of the same dimension, you actually need to prune this neuron 2 simultaneously. And we call such a network as a multi-branch network. So if you are aware of models like ResNets, those are multi-branch networks, whereas when I introduced initially a single branch network, those are VGG type models. So such type of connections make it very difficult to prune uh, neural networks, and this has been uh, a rising trend in the pruning community to kind of work on, because this is a hard problem to solve, because this in itself looks like a simple diagram, but when I'll show you an actual subnetwork of ResNet 50, which is one of the simpler versions of neural networks that are used nowadays, you'll see how complex it gets. But why do you want to target pruning this network? So what we found out is that more than 66% of the inference time in a model like ResNet 50 is usually consumed by such layers, and people in pruning community until very recently did not even focus on pruning such networks, and the inference time speedups were very modest. uh, and I'll show you empirical results of them too, but that was it. So coming to showing you how quickly it can get very complicated. So this is a subnetwork of ResNet 50, and uh, how do you capture the notion of this coupling for pruning? So until this work, it was unclear how you even formalize the notion of what can you prune together. So towards that, we propose the notion of data flow couplings. And so let's say that you want to prune one neuron coming out of, or one channel coming out of this particular layer. So to actually prune that channel, what you actually have to do is prune all of the channels that are marked in red. And this quickly got a little too complex, because you now have to keep track of what's to be pruned, what's not to be pruned. And while it looks that this may be manageable, uh, this actually becomes a big headache when you actually want to automate pruning models at scale. So today you got ResNet 50, tomorrow you got ResNet 56, maybe later you got a llama. uh, how do you do that? So this is quite hard to automate. So what's that? We just rearrange these layers. What we say is, if we just rearrange these layers, uh, what we say is, the layers in pink, we call them feeding layers. The layers in cyan, we call them feed out layers. And if you look at it, all of these transformations that happen in between, this could be batch norm layers, this could be sigmoid ReLU layers, this could be additions. They are all element-wise transformations. So if you have two vectors A and B, the output of any transformation, say C of I, would be A of I, uh, a function of A of I and B of I. The same elements would be used to compute the output. Uh, right. So we mathematically formalized it, but this is the core idea of it, that we just restructure them and provide it a mathematical formulation to do theoretical analysis on this. So formally we say that tau, which is a triplet of or A, B, and F, which is where A is the feeding layers, B is the feed out layers, and F is the element wise transformation. This is a DFC if F only consists of element-wise transformations. The data flow graph forms a single component. So this should be a single component if you think of it that this as a graph. So all the layers are nodes, and the connections or data flow between them is an edge. Uh, and the third is, with using the layers of the neural network, no larger DFC should be possible. So this basically ensures the completeness and exhaustion of coupling in a network. Right. So this was the formalization of data flow coupling, which was our contribution. Now, why do we need this? Because such structures are very poorly understood, and formalizing it helps us do theory on that. So, uh, before when we introduced our structured pruning, we saw that we assign score to a single neuron. But now, when you look at such a structure, it's very hard to uh, kind of identify individually which particular neuron or channel uh, would be pruned. How do you decide which neuron or which channel is important in this entire structure? And so a hypothesis, a very stupid hypothesis here would be, oh, let's just take this layer, see what is important for this layer, and then just discard it for all the layers. Uh, but would that actually work? Uh, so through this experiment, what we show is it actually does not hold true. So how do we show that? So let's say that this was a DFC, that the output of these two layers were fed into a residual connection, and that was an input to this layer. So what we show is, if you pick a single channel, so channel I from here and channel I from here too, and by definition of a DFC, these two should have the same number of output channels. Uh, we measure the difference in rank of importance that channel I would have for both of these layers. And how do we do that? We use traditional saliency measures that were there in previous work to kind of rank channels or neurons in a neural network. And we found that for most of these uh, indices or neurons, the disagreement in score, which is the difference in the ranks, was pretty high, which basically means that uh, if channel 14 says that, say, the third neuron is the least important for me, layer 15 would say, hey, the same neuron is the most important for me. So if you want to prune that, I won't allow you to prune it. So to mitigate such disagreements, we would actually need to make a cumulative uh, analysis of what is actually to be proved. So such sort of importance scores or and importance saliencies is just a synonym for importance. So such sort of saliencies, we call them group saliencies. So group saliencies are saliencies that jointly compute the importance of what is to be proved by taking a consensus from the feeding layers, the feed out layers, and the transformation functions. So yeah. So what this said is that the traditional methods, the way the traditional methods used to compute scores of neurons, that no longer was too useful. So now that we have this, can we build an importance score to measure uh, the importance of a channel without access to training data, right? Uh, can we? Now, to do that, we propose an algorithm called the backwards graph based saliency computation. So think of this as a forwards graph of a neural network. And what we do is we just walk through, algorithmically walk through in the reverse order to find the saliency scores. So let's just focus on this part. What we'll do here is we'll initialize a vector that we call the accumulator vector using the weight of this layer, weight of layer 16 times and a vector of all ones. So dimensions can be appropriately handled. And we now go backwards. So at every residual addition, the algorithm says do nothing when you see a residual addition. When you see a ReLU, use the Lipschitz constant of the ReLU operation uh, and pre-multiplied with the accumulator vector. So this is basically an identity matrix for the ReLU operation. And yeah, for a batch norm layer, use its Lipschitz constant. Uh, and once you encounter a feed-in layer, you basically perform this particular operation. So as you go from the feed out layers to the feed in layers, when you perform these steps, you get the accumulator vector for one particular layer. When you repeat this for all paths between every pair of feed out and feed in layer, what we show is the net error that was to happen when you discarded something from all of these. So if you're removing channel I from this particular DFC, what would be the net error that would occur here? That could be upper bounded by just the magnitudes of the accumulator vector. And why is this important? This is important because you are trying to estimate the worst case error of pruning that would occur here when you pruned something without actually having access to the data, which is why this is a data free scheme. So we basically measure the saliency of a DFC's kth channel. So k channel is coupled using the sum of all the accumulator vectors that you get across all the paths. Uh, right. So this is the saliency that we use for our pruning algorithm, and this is data free, and these are the empirical results. So when we do not fine tune, uh, we see that, and our method is called DFPC. We see that we are significantly much uh, we are producing significantly much sparser models with better accuracies without any access to any training data. And this is a big win because you can see how far the baselines could be. And since this was the first work in this space, we did not have very strong baselines to fair, but we made significant progress here. Uh, yeah, and the more challenging space comes when we actually fine tune, and there are tons of work that do this, and uh, this had a lot of investment in big tech too. So when you actually compare uh, what happens when you prune couple channels versus you don't, there's a very good insight here. So first of all, if you look at this version of our pruned model, which we pruned for 30 iterations, uh, what we see is, let's say for a model that had an ImageNet model that had 75.9% accuracy, you could see that so this was a pruned model from Microsoft Research. So it had a 74.7% accuracy, but it had larger number of reduction in flops and parameters than our model. But despite that, just because we focused on pruning couple channels, we had much higher speed up in GPU and CPUs. If you compare with this particular model, we almost have comparable accuracies. While we have larger flop and parameter reductions, the speed up is just, uh, if I remember correctly, it was at least 47% faster than all of the baselines that we had. So The takeaway here is prune coupled channels. Just pruning them smartly would help you get much faster speed ups to make your model inference quite faster. Right. Uh, so the takeaways again, pruning couple channels is critical. The second one is one requires group saliencies, and the traditional way to measure importance of neurons do not work for pruning couple channels. Third, flops or number of parameters do not strongly correlate with the latency that you would observe when pruning a network. And DFPC does a reasonably good job to prune in the data-free regime. So these were the kind of takeaways that we had from this particular uh, work. Uh, I think we're done with the first part. If you have any questions, I'm happy to answer. Okay. Okay. Then let's move to the second piece of work, which is to understand without access to training data. Uh, how so here we had this algorithm called the BGSC algorithm to kind of understand what uh, neuron or channel is important to prove, but what can we do something different and something better. So the question that we had is, uh, let's say that you have a classifier that classifies cats and dogs, but you actually don't have the training data set for that classifier. What if I could go outside my lab, find a cat, find a dog, click their pictures, and use that data to prune the network? Would that even be feasible? So, along that thing is how we started thinking about the next work, which is uh, it's again a handful of a name, uh, but I'll come to every bit of it. But the paper was called TVS Prune. So the idea is, let's say you do not have access to the original training data, but somehow you are maybe able to generate synthetic or similar samples of data to your original training distribution. Would you still be able to prune? And if yes, how would you decide what is to be pruned? So we thought of a very straightforward way of kind of dealing with this. So what we thought is, let's say if you have a channel that takes in an image of a cat and image of a dog, if it generates similar distributions for both of them, and why we are talking of distributions, because we actually do not have the original samples. The only thing that we can compare are distributions under the assumption that the sampling that we did from our own camera is similar to that of the original samples. Uh, so if both the distributions that were generated by the cat and the dog were similar, then I think we should be able to prune this particular filter. And if not, if the distributions are different, we might not be able to do that. And we made a hypothesis that well-trained models, that is, models that are trained to almost convergence or convergence, possess a mix of discriminative and non-discriminative filters. And we validate this hypothesis, but given this hypothesis, our pruning strategy is to identify and prune non-discriminative filters. So filters that do not discriminate between the distributions of the different classes that you have. So how do you even know that we have this picture, right? This looks straightforward, but you actually cannot measure if two distributions are separate because this is a very high dimensional vector. So what do you do here? How do you actually figure out which uh, filters are discriminative and which are not discriminative? So the idea that we used is to use statistical divergences, and the one that we tried to use was total variation distance. So total variation distance just measures the uh, divergence between or distance between two probability distributions. And what we do is, so how is this defined? It is basically the suprema or maximum, not technically maximum, but maximum of uh, the probabilities that you get for any event A in the probability distribution. So that is how that is defined. And we define the discriminative ability as the TV distance between the distributions of classes alpha and beta. And we take the minimum of pairwise comparison for all classes. So if you had 10 classes, you would do 10 C2 comparisons of computations of TV distance and select the minimum one. Uh, However, the problem is that TV distance is hard to measure from samples. You cannot measure that from samples. But the good news here is there was a lower bound to TV distance that we actually used, and that can actually determine the uh, distributional divergence using a few samples. Uh, and I'll tell you why that was a good thing uh, and a bad thing. So bad thing because the lower bound has an implicit assumption that uh, the data distribution is Gaussian, which again we cannot validate because the vectors are too high in dimensions, uh, and we do not have so many samples to validate it. So this was an assumption that we partly said would work because we were sampling, uh, but the good thing is how this is defined. It's that it just uses the means and the variances of the distribution to kind of uh, find the distributional divergence between the two distributions. So from the mean value theorems, you would know that if you have an estimate, a sufficiently good estimate, or a sufficiently good number of samples, uh, you could actually lead to the mean with a reasonably fair chance. Uh, so having with that assumption of Gaussianity, this could actually be a good estimate. But we need to validate that. So first of all, do discriminative filters exist in well-trained models? That was the initial hypothesis that we had. What we show is, let's say if you have a pre-trained model and you try to perturb the weights with random noise, and as you add more variance to the random noise, we see that if you this is the trained model, as you add more random noise to it, the accuracy actually decreases. So it actually says that the mean as you add random noise to it, the accuracy decreases, and with decreasing accuracy, you see that the number of uh, the average TV separation or the separation measured by the Hellinger distance actually drops. Uh, and this actually suggests that a well-trained model actually has a good set of uh, uh, discriminative and non-discriminative filters. Okay. Now, now that you know what is to be pruned, an additional challenge is how much should you prune from each layer? And deciding this is a little hard, but the good news here was we could use the same idea and convert it to a format that could help us identify what is to be pruned. So we define what is called as the LDIF score, which is a product of the fraction of discriminative filters and one minus of that. And what this actually shows us is that uh, LDIF score changes with layers. And what this shows is the initial layers are actually quite hard to prune, and the later layers are a little easier to prune. So this helps us decide. So if we had a budget that we wanted to prune 30% of the uh, weights to make the model fit into our GPU. This particular score could actually help us identify how much is to be pruned. If I have a 30% budget, how much should I allocate to each particular layer? So this was one more good consequence of this particular methodology of looking at the importance of a channel. So this was the main algorithm. You first compute the mean TVS score. So the difference between the iterative version and the normal version is that we perform this step multiple times. But the core idea is you compute the TV separation between the channels for each class, get the mean TVS score, uh, compute the LDIF score, and if the LDIF is lower than the threshold, then you select what is to be proved. Uh, right? Uh, so as simple as that. So, okay. So once you use this pruning algorithm, so the experiments here show iterative TVS. Uh, so we achieve again. This is again a data free, not technically a data free thing, but we do not use any fine tuning for any of the baselines. So for the example, this is one of the strongest baselines out there, which uses the gradients of the training samples to kind of identify what is to be proved. And until a parametric sparsity of 20%, we're neck to neck, but post that the Taylor first order approximation drops, but we were actually quite better. And with respect to other state of the art methods that kind of line no fine tuning space, we were also able to kind of marginally improve on that. So, and these are for ResNets and ImageNet scale, so that's pretty good too. Uh, yeah. So the takeaway from this particular work was that the discriminative filter hypothesis actually holds true, uh, which is quite surprising because it basically says that since the initial layers to the final layers, everything has a discriminative, not everything, but a fair share of things have discriminative behavior that helps in prediction. And uh, we also show that without access to training data, we can actually use the statistical moments, which are means and variances, to identify what can be discarded and how much to be discarded from a neural network. And yeah, TVS spoon works reasonably well when fine tuning is not possible. Yeah, so I think I'm mostly wrapped up with the presentations I had. We have follow-up works on top of this, but yeah, this is what I wanted to introduce, which is basically the space that we are working on, which is pruning without having access to the original training set. Yeah.